Okay, so we're trying to complete the first section of Chapter 3. And Chapter 3, again, is particle kinetics. And particle kinetics dealing with the second law. Tomorrow will be, I think, the last lecture on second law. The following week, we will talk about, or next week, we'll talk about work energy. And the following week, we talk about momentum. And then you have reading week. So everything's moving very quickly. The thing is, you're going to do the same thing you've done before. I'm actually going to not use 3 dimensions here. So the whole goal of writing and doing all of these various types of free body diagrams is to break it down into components. So yes, your governing equation is sum of all forces is equal to the mass times the acceleration of the particle, which can go in any sort of direction it wants to. For now, I could add in an Fz and an MAZ term. I'm just not going to because we don't really deal with them here. And so the scalar, the component equations we'll look at are just going to be the sum of forces in x, mass times acceleration in x, sum of forces in y, excuse me, equals mass times acceleration of y. For completeness, and this becomes more important in Chapter 8, we can write that as sum of forces in x is equal to mx double dot, sum of forces in y equal my double dot. Those are our governing equations. Those are our diagrams. So you see the diagram, the second diagram down on the left. You'll notice force 1y. There's another force 1 or force 2y in there that I haven't properly sort of labeled. Force 1x, force 1 or 2x. You can add all the forces together, and again, the tricky bit is not to solve the equations. Once you have the equations, you're set. It's just putting together the right free body diagram. So that's where you start. Now, in dealing with nt coordinates, you're just going to write sum of forces in the tangential directions are equals mass times acceleration tangential, and sum of forces in the normal direction are going to be mass times acceleration normal. And here, for example, is a free body diagram showing a bunch of normal forces being summed, a bunch of tangential forces being summed. And over here, mass times acceleration and mass times acceleration in the 2 directions. And I got them right. And so your problem always comes down to the same thing, which is just writing the correct acceleration and the correct components for each problem you're dealing with. And again, often in this course, you don't get much choice. We tell you use xy, use nt. But outside, when you do your own work, you are going to end up in situations, and this is often more convenient. All right, which one do I want to do? Yeah, okay. All right, so so one of the things that you certainly love at this point is everything to do with section 2.8, which is absolute dependent motion. And here we have a problem that's kind of interesting in the sense that there's a relative motion between the two objects. So I have a ramp with an angle of theta equals 25 degrees. On there, I have a mass A, which has 40 kilos, and mass B, which is 8 kilos. The coefficient of kinetic friction between all surfaces is mu sub k equal 0.15 and mu sub s. So coefficient of kinetic friction of 0.15, coefficient of static friction of 0.2. And again, this is what you expect. Mu s is always going to be greater than mu sub k. Find acceleration A, which is the tension in the orange cord. So I'll start by something simple, which is just that length constant. I know that the distance between A and B is just a vertical distance, and it goes from a point on block A and it goes to a point on block A again, and that distance isn't going to change. I'll just call it L sub C. I don't really worry about that too much. I can call the two bottom lengths X sub A, because those two bottom lengths, again, they're going to be associated with A. I'm going to skip even dealing with this little tiny bit here. It's another length constant. So when I do my addition of the total length of this cord, I'll just sort of ignore everything that is sort of wraparound length and things like that. What I do have also is this top bit. And that's a relative motion, xb relative to A. Because A is going to move, I kind of expect it to move down the ramp. B is going to move up the ramp. I was kind of thinking about it intuitively, I might be wrong. But in which case, it's a motion not with respect to the stationary frame, the ramp. It's with respect to the block A. So if I link all of that up, I get this. I get 2xa plus xb with respect to A is equal to length total. And when I say length total here, again, I'm combining all of these constant lengths. So this constant length, this wraparound length, this wraparound length, this right here, and that wraparound length. So all of those constant lengths aren't going to change over the over whatever motion occurs. I also know that the acceleration of B is equal to the acceleration of A plus acceleration of B with respect to A. And I only care about acceleration at this point because what I'm interested in is my second law analysis. So I have that, I have this, I have all of these terms here. Ooh. Come on. So I can start to look here. So I have normal of A on B, which is from that lower mass onto the block. I have MBG. I have the force of AB, and anything else? Tension. And I have defined my coordinate system, IJ, which is also XY, of course. I have all the forces acting on there. Yeah, okay. So this is this should be FAB is a friction force between the two, just so you recognize what it is. And I'm expecting, again, intuitively at this point, that B is going to move up the ramp, and so the friction is going to oppose the motion. Normally B, all the forces there, everything's good. So sum of forces in Y, let's do that in a different color. NA minus, NAB minus MBG cos of theta is equal to 0. NAB equals MBG cos of theta. Force AB is equal to mu sub s NAB. Force AB, sort of substituting in numbers, will equal 0.2 MBG cos of theta. All right, so I have the friction force. I'm going to sort of write this down because later on I'll forget. And it's hard to remember if you look at my notes later and try to figure them out. Yeah. So I'm assuming that I'm going to have impending slip. And if you remember, there is no slip when the force of friction is less than, not equal to the force of the mu sub s times n. Impending slip when you have force of friction equal to mu s times n, so I'll put that in as a guess. And finally, slip when it's going to equal mu k times n. So minus t plus FAB plus MBG sine theta, and the tension is equal to MBG 0.2 cos theta plus sine theta. So just substituting in the terms, I have FAB over there, so bring everything over to one side, and I should say that's equal to 0 because at this point I'm assuming no motion, and if I assume no motion, MA equals 0. Then T on the right-hand side, I have a function, or I already know what FAB is from the previous part, and I can sort of tie all of this up together with cos and sines. Wrong color. So I have to look at what's happening here. But if I look at my pulleys and I wrap them around, I have the two links. The pulley cord is attached at the bottom. It goes, wraps around, comes to the first pulley, then goes around again, then comes out on top. I have normal of A. And from Newton's third law, I know that that internal force, when I separate out those two bodies, NAB equals negative of NA, or NAB equals negative of NBA. So if you look at the very top there in the upper left, I have it pointing up, and when you look at it at the bottom, I have it pointing down. Okay, let's see what else we have. Now I have, because I've separated out the system, I have the friction force FBA, which I've already solved for, and FA, which I haven't solved for. But I do know what the magnitudes of terms are. And again, sort of a little a system that aligns with the body I'm looking at, and I get sum of forces in y equals 0, and from that NA minus NBA minus MAG cos theta is equal to 0. And A is equal to MA plus MB G cos theta. One thing you should notice at this point, just 1 second, is that I have not included directly the weight of block B. I've transmitted the weight of block B, or the components of block B, through that normal force. Go ahead. I did. Thank you. But remember, again, it's all, as you separate out these bodies, you can do whatever you want. You can look at one block or the second block, but as you're looking at both of those blocks, if you separate them, you have to consider all of the forces so that if I add them together, everything goes to 0. So the other side to this, of course, is sum of forces in x is equal to 0. Again, impending slip. Okay, so Very little manipulation at this point. You really are just, once you have that free body diagram, no matter how poorly you draw these things like me, you still get a lot of information out of it. Go ahead.
So far in questions, right? We're assuming like the body, the dimensions, like with the point where the forces are, don't matter, right? Like we're assuming like they're not rigid bodies, right?
So they're not rigid bodies. That's chapter 5. You're right. I draw them this way so I have something to look at as I'm doing things. And I have noticed in Piazza people sometimes draw particles when they're dealing with boxes and things like this. I strongly recommend you draw it like this, even though there's no rotation and it is not a rigid body at this point.
Why is the top tension force on block A, why is it completely like horizontal? Because in the picture it's kind of on an angle.
Which one?
The top left.
On the green one?
Yeah.
It should be aligned with this. So if you look at the image, again, in expert drawing, it's also aligned with the top of the block. So it's parallel. Just one second. Okay.
In the second FBE for the A block, I understand why we include the bottom left tension force, but for the two tension forces above that, they're not actually connected to the block. So why do we consider them?
So you're talking about this one and this one, right?
Yeah.
So those two tension forces are acting on the block. So if you look at the block itself, it's attached, again, very poor drawing on my part, but you can see those two circles represent the original pulleys. The pulleys are attached to the block, and that's why you're seeing that force transmitted. Yeah. Okay, no problem. So I have an expression for t. Actually, I have an expression for t. I have an expression for t. So I have two expressions for t there, so they have to be equal because it's the same tension. So let's see what happens. Actually, I'm going to move over a little bit more because I need to go back. So G 0.2 cos theta plus sine theta equals G ma sine theta minus 0.2 ma plus twice mb cos of theta. Okay, putting all that in, I'm going to end up with tan theta after some manipulation of 0.4, and theta equals 21.8 degrees. So one important step as you're dealing with slip, no slip problems is you always start out with the assumption of no slip. But in this case, in order for no slip to occur, I have to have an angle theta which is less than 21.8 degrees. Since I don't, because the original angle I was given is 25 degrees, this is a slip problem. And that's how you check. You don't presume at the very beginning that you have slip or no slip. You presume you have no slip, solve through, and then you solve again. So the nice thing about OneNote is I can scribble away at any section I want to and just keep making it bigger. All right, so now I need to look again at this problem. And so if I look at this problem, I have the free body diagrams that I already drew. And so I have MBAB. I have XY here. I have normal AB, MBG, FAB, and T. One thing hasn't changed. This thing is still not jumping or bouncing. And so sum of forces in Y is still going to equal 0. So I have all that. So, and this is just equals. So this is your kinematics. And I don't always draw the kinematic diagram, but it's useful to sort of remember that. I'm just setting up the Newton's second law just so I can look at it. So in terms of everything that I have done before, I still have NAB, which is equal to MBG cos theta. I have, from that, my friction A to B, which is on my diagram. But I know that instead of using mu sub s, I'm going to use mu sub k. Mu sub k is given to you as 0.15. And it's MBG cos theta. Now, we have slip at this point. So the difference is in my so the thing you often depend on is that there's nothing moving up and down relative to the ramp. It's just sliding along the ramp. But you do have slip. And so you now have an acceleration component that's acting in the x direction. So now you have an expression for tension. Again, tension has to be the same in that cable all the way through, because if it wasn't, the cable would be stretching. We have inextensible chords in this course. So one of the primary assumptions is that these chords, these pulleys, never change length, and there's nothing to stretch them. And they certainly can't have different forces in them, otherwise they transmit different things and sort of blow up. So if we do the same thing, we have tension, tension, we have tension, color those differently. Tension, tension, tension. BA. And xy. So we have x going down the ramp again, y, same thing. We have all of the same forces, but of course the magnitude of those friction forces changes. And again, the friction forces are acting parallel to the surfaces no matter how I draw them. I guess that's. So sum of forces is equal to y, or y equals 0. NA minus NBA minus MAG cos theta equals 0. NA MA plus MB G cos theta. Force of friction is equal to mu K NA, which is equal to mu K MA plus MB G cos theta. All right, I'm going to have to still blow that up. Yeah. So sum of forces in x is equal to mass times acceleration, or mass of A times acceleration of A. And again, notice that I haven't really transmitted the weight. I've transmitted the normal force. So block B's effect on A is through Newton's third law, not a direct calculation or an inclusion of that force, because I've defined it as two separate bodies. Okay. So adding all the terms up, putting everything together, separating out t, you end up with this expression right here, which is kind of a mess. But as before, where did I put my second t term? My t, 3, and this is 4. 3 equals 4, and acceleration of B is equal to minus 0.9875 meters per second squared. (51.7 newtons). Okay. And I've kind of carried it out. It really, if I wanted to write it at two significant figures, if I was worried about it, I'd write it as 0.99. Generally, just that should be fine. acceleration B, tension in the cord, everything is calculated once you have the free body diagram. The hard part is drawing the free body diagram. This is a good problem for you to try on your own because there's a lot of things happening in it. And I kind of blew that one up. There we go. Any questions? Go ahead. Yeah, I never used it. I probably should have solved them. So at the very beginning, all I did was I wrote the acceleration of B is equal to the acceleration of A plus the acceleration of B relative to A. If I was asked to solve for the acceleration of A, I think I was solving, which one did I solve for? Yeah, I just solved for B. If I wanted to know what the acceleration of A was, I'd just subtract off B with respect to A. I am calculating the acceleration of B with respect to A, but I'm not using it in this part of the problem, or in this problem. But it's a straightforward next step.
Why did you use the other constant for friction to find the angle when you want?
So one of the things, just one second. One of the things that I was asked is, I have a ramp at 25 degrees, but I was not told in this problem, and you're usually not told, whether or not this thing starts to slip. So I need to determine at what point does it slip. And in order to meet all of the conditions there, I have to set T equal to T, because it has to be the same tension all over. So for that to happen, I found that the maximum angle was 21.8 degrees. So that tells me right away that that's going to move, and that the lower block is going to move down the ramp because it's heavier, much heavier, and there's a lot more force. Even with the multiplication force, it's 16G versus 40G if you look at the wraparound of the pulleys. That tells me you have slip. So at that point, I have to redo the entire problem. You'll notice I drew all of the free body diagrams. I rewrote all of the equations from the beginning. However, I didn't need to do that because all of the equations were exactly the same, except that instead of mu s, I was using mu k. And then I did the solution again.
Is that what you used when you drew the free body diagram for A when you pointed FA towards the left?
Which one? So FA is the friction force. No. But FBA, you'll notice again, is opposed to FA. FAB is opposed to collinear and equal in magnitude, but opposite sign to FBA. And so if I snap this together like a Lego block, those forces would have disappeared that are internal. So any force that I put in that is common to the two but opposed to each other are internal forces if I look at both blocks at the same time. Yeah. Sorry, this. Ooh. Okay. I don't. I mean, I don't. Oh. Yeah. Everything will flip. What did I do? What did I get? Oh, I have an acceleration of B, which is negative. So it was in the opposite sense that I expected. That's why it sort of works out. And if you have correctly considered all of the forces, I know that people will tell you different things. If you have considered all of the forces, a single force that is out of line in the wrong direction will not affect your calculation. It will correct itself. However, if you have multiple forces in the wrong direction, often it causes more confusion and things get messy. So it's not a perfect system, but it's not a bad system. So as much as possible, and this is why when you look at this particular problem, all of the calculations are easy. This is hard. This is very, very hard. So you're going to spend a lot of time drawing free body diagrams, and you're going to spend a lot of time making sure you have all of the forces, and also how to relate them. So if you go back to the kinematics, you need to recognize, for example, that one block on top of another becomes a relative velocity. Go ahead.
If you go to the equation that you labeled as number 4.
Yep.
Would the last line on that, would that be a negative?
No, I think it's correct. You're bringing, oh, maybe it is. I don't remember. I'll have to check and see for sure. It's not, the answer's correct, but I often will make strange typos as I write.
When you compare equations 3 and 4,
Yeah.
in the final term, you have MAAA here, and then for number 3, it's MBAB. Aren't those two unknowns? Like, how do you compare them to each other? With the relative motion.
You have them with the relative motion. I will check and make sure I have everything correct on that, and I gave you all the information. I may have missed something.
Because with relative motion, would A be in terms of
Yeah.
A or vice versa?
I have to check and make sure that I actually gave you everything you needed. So I'll go back to that one. Anything else?
What if you screw up and you mislabel the direction of the forces on the free body diagram?
If you mislabel 1, it'll correct itself. If you mislabel 20, you will not get the right answer. So the answer to that question is you have to be really careful in setting up these problems. So adding the tensions, considering all of the directions is really important as a first step. Okay. Go ahead.
I can't really see why it would correct itself, because like, with the friction forces,
So
if we're in the wrong direction, we'll just flip. But like, our tension is still in that direction, so would that not have an effect?
So the tension, for example, I know the direction. They're always acting in that sense. If you look at this particular example, I had miscalculated the direction of the acceleration.
Yeah, so if you go to, say, the sum of the x forces for the B diagram,
Yeah.
right? Like, yeah, the one above.
Yeah.
Like, the equation relates the tension and the acceleration of B, right?
Yeah.
As well as like the friction forces. Like, since A is in the wrong direction, the friction forces will flip. But
Yeah, but I actually assumed it in the right direction, right?
right, but then our equation would be different.
Our equation will be, the result of the equation is, no, the equation I gave you is still the same. It'll still end up being what it is. It's just the acceleration. In this case, the one error I made in terms of drawing it is saying it's coming down. That or the acceleration B. So that correction will occur when I do all of the force balances. So my answer will have a minus AB instead of a positive AB. These things require a great deal of time. And no amount of drawing will convince you. Okay. Really quick, I'm just going to start one. I'll probably continue it tomorrow. I don't know how long this will take. Oh, I'm jumping a little. All right, I'm going to just do this one. No surprises here. Sum of forces in R equals mass times acceleration R. Sum of forces in theta equals mass times acceleration in theta. And so I have here a semi-cylinder, and what's happening is a small block or ball is at rest at the top of a frictionless semicircular surface. Ball is given a small nudge, so it slides along the surface. At what angle, theta, does the ball separate from the surface? All right. Again, when you look at problems like this, one of the biggest problems is you try to imagine all sorts of things happening. Don't. You're just solving it at this instant, and at this instant, this is what's happening. So you have weight and a normal force. That's it. And you can define r theta with respect to the center of the circle. A reminder, in this particular problem, there is no change in r. This is going over a circular arc. That r is not changing with time, so r dot and r double dot will equal 0. So ar is equal to minus r theta dot squared. Same thing with the acceleration in theta. So you're dealing with a subcategory of a standard problem, which is that r is not changing. So I've got weight, I've got all of terms, I've got r and theta defined here, and I have the acceleration terms. So in this particular case, what you have is a normal force that's acting in the r direction, a component of weight which is acting in the r direction. You've done a lot of coordinate transforms at this point. And that's mass times acceleration r, which is minus r theta dot squared. Force in theta, mg sine theta, which equals ma theta. I can rewrite that second derivative and say, well, using the chain rule, it's d theta dot d theta dt, and d theta dt I already know to be theta dot. So I end up with d theta dot d theta, and what I want you to think about is it's the same, or the analog, for angular motion, for linear motion with acceleration, so v dv ds. I got 28 seconds to finish this. So with all of the extra time that you have, you can